Hello everyone. So in this lecture I will be explaining the modular inverse and binary exponentiation. So let's start with the binary exponentiation. So we begin with the problem that we would like to solve. Say we'd like to compute a to the power of n. Mod n for this to be a bit more accurate. So we want to find the exact remainder. So, like you can find in other literature that sometimes they use the mod and the remainder it's like instead of each other. So you just have to make a small distinction between the remainder operator and like the congruence, the modular congruence. To say like two numbers are congruent even if none of them is the remainder or anything. So here we'd like to compute the remainder. So here we can do as follows. We can have this m as a number represented like this, or so it depends if m is even or not. So here, to compute a to the power of m, remainder of n, this we can compute like a to the power 2 for m. We multiply this for a. Sorry, this for r. And here we can compute this. And from the modular arithmetic, we know that we can make this. So we can compute this part and make it modulo n, and then we can raise this new mod to the power of r, and also after that take another remainder operator and so on. So because we said we could always make any groups of multiplications so we can exchange any number by its remainder. So we can even group some numbers to multiply together and take each of them, put its remainder, and then we multiply everything and then get another remainder. So for us, it doesn't matter, we get the same result at the end. So basically it's like that. And so this part you can say it's like the number n. So r then times a, the number n. For this section, and for this part we have a squared of the remainder n. Yeah, I think now them stick this, or this should be r. Yeah, so this is the basic idea, and we can code that right away to see how it is from a computational point of view. Here we call it like power mod, so taking an nth power and then making a remainder operator. So this xp or dx, this is the exponent, which is the m in the equations I explained. and this is the uh, here if the exponent is 0, you return 1, and if the exponent is 1, return 1. Technically we should be making that, but it shouldn't matter. But if it will only matter if the mod is equal to 1, but it's a silly case anyway. And then here we have this part. So this is the a squared. And here we e. So this when we take so here we divide the power by 2, and I floor this, so it is this r regardless of what is the remainder. And then we check if the number is odd, then we multiply times a time. And here we should take care when to cast any multiplication to a long end just before we make the multiplication, because this multiplication here might make an overflow bar. So we need to take care of that before we make the multiplication. Then after we take the mod, again, it becomes back a small number, so it's not a big deal. Can be like that. The other way would be so this can be e to the power of r, and then we can and as I said, we shouldn't forget the casting. So this one is the same here, but I just made it like this part, the a for 2 all to the power of r. It's the same like a for r all to the power of 2. So it's the same thing, it doesn't matter the order, how we do it. We can start testing them. Here I'll use both functions to just show the result. Yeah, that's very nice. I have to compile it properly, and we can run. Here you can see the powers of 2, as we expected, and they're all, so we'll take in remainder 1,000,003. So until here it goes as expected, and then the number after that is million something. So basically it starts to go down again, and so on. The sequence stays. So basically this is the sequence, and here we see that also the other function is getting the same numbers. So yeah, this is basically the binary, what's called binary exponentiation. So the reason I would use something like that is mainly because of its time complexity. It's much more efficient than the normal one. So the normal multiplication would do O of m multiplication. So the normal would do O of m. So unless I need all the m multiplications, which can happen in some of the problems, sometimes I need all the powers of some number, so I pre-compute them. So in that case, yeah, it's better to use the iterative way because we already have a recursion for it, and so we can compute each each of these powers in O of 1 by using the power before it. But if we just want some distinct value, here we have this binary exponentiation. This is done in order log m. Because here we can see that the number of operations we do, or the number of multiplications, you see that we have here 1, and here we have 1 from this a squared, and then we'll have what comes out here. So basically it's like that. So this is like 2 plus m over 2. We find that it's equal to log m. Log m. And this part is t of 1, which is a constant, so basically that's both of them. So that's the time complexity of the binary exponentiation. The way I personally write it is in an iterative way, or something like that. I begin with the result equal to 1. So this is the a to the power 0. And then I still have exponent. Like here we can also estimate quick notice. So uh, the EX shifted 1. This is the same value. We make x divided by 2. So here, because this we shift the number to the right by 1 bit, it means we have it's the same as we divided by 2 and 4. So usually this is a good technique for making like the operations faster, because the shift operations and the bitwise operations are usually much more fast than the multiplication or division. So if you want like a power of 2 or divide by 2 or take modulus for some power of 2, it's all good to make it with the bitwise operation. It's easy, but otherwise we will use the normal operation. Yeah. So basically here, this loop goes over the number of bits that we have in the number, and it keeps squaring the a every time. So technically speaking, if we have here something like type 0, here 9, here we should have the restatement. Now a is equal to the first a. So this is the original a that we have. So we should always have here that the ith step of this loop, we have that the a now is equal to the first a, to the a0 to the power of 2 to the power of I. And then here we check if this corresponding bit is equal to 1, then we multiply this a by the result. Basically, you can think of it by computing this. A to the power of so here we want to have we wrote here the powers. This is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So here we want to have this. So this is 2 to the power of 10. Yes. Like we use to convert this binary number to its power exponent version. So it's represented something like that. 6 and so on. for 4 to the power 2. So this is equal to 2 to the power 10 times, I think I'll make this a, make it quite nicely. So this is a to the power to the 9, a to the power 2 to the power 7, and so on. To the power 2 to the power 4, a to the power 2 to the power 3. So here we can see the binary exponentiation, how it goes and so. Basically, yeah, so here the ith step of this loop. So basically we're looping at these numbers. We find like each of these numbers is, so we want this number, basically e2 or I times 2 for I squared. So each of these are the square of the one before it. So basically we go here to all the numbers, all these powers, this power 1. So here we find that the exponent has 0 bit, like here. So basically we don't do anything. So this part is, we don't execute it. And then we multiply a times itself, is seen here. We shift the exponent to by 1, so as if we remove this. And then we can, so we're here, we check, we don't find the bit to be 0, to be 1, so just do nothing. Here we find it to be 1, so multiply this term now by times the result, and then we have this one, but we do nothing. And here we multiply by this value, and here we do nothing, and so on. So we keep going until we multiply by all. Basically, that's the idea of the iterative version. So we can this should be here. I had the condition wrong in the beginning. So here we should check that the initial power, so mean the original a to the power 2 power I is equal to the current a that we're actually initiating here. This part. So basically this is the code and it is running properly. First, so as you can see, it also computes all the powers. As you can see, and at the million something starts to get back small numbers. So this is the overall idea of the binary exponentiation. Okay, so now I move on to another topic, which is the modular inverse. So basically, we want to solve the problem. We have some number a. We would like to find a number b such that a is, times b is congruent to b times a, congruent 1 mod n. So basically, we want to find a number b when we multiply it by a, so the product is equal to 1. So this is the definition of finding an inverse. So b basically is the one inverse. And then. So there are two ways of finding this. So I will explain the more general way. So the first one, we start with we have the a and n. Basically, those are our input. So we have the Bezout's identity. So here we have this a we can multiply it by some coefficient k1, and this k2 times n. This will be the GCD between both of them. So the both number here are coprime. So we have this GCD will be equal to 1. And here we can find this k, or so the k2. So using the extended Euclidean algorithm, here we can get these k1 and k2. So let's assume that we got them. So we make this equation modulo n. So this part will be 0 modulo n, k1 times a, congruent to this GCD n and a, which, as we assume that the GCD between both will be 1, because they're coprimes, so we will have this part modular. So basically, this is how to find the inverse. So we find it from the coefficient of a when we make the extended Euclidean algorithm. This is the first way. The second way, we can solve it if n is equal to some prime. If we remember from one of the previous lectures, we had this identity that a equal to p minus 1. That was in the modular arithmetic factor. So this is congruent to 1 mod n, mod p. So basically, if we have, and we still assume that a and p are coprime, in that case, the a times a to the power p minus 2, this is equal to 1. Or congruent to 1. So as we can see, if we can calculate this number, we can easily find the inverse of a. Basically, this is a number that satisfies the definition that when we multiplied by 8, the product is 1. So how do we compute this number? It's using the binary exponentiation we had earlier, just called the tau mod function. a times, power of p minus 2, and we take that multiple. So this is the inverse. We can still solve this problem if p is even not a prime number, but still if a and p are coprimes. I will just mention it here, but I will not explain it why it's the case. So there's a generalization of the Fermat's little theorem. It says a to the power of n 0.1 mod n. This phi is called like Euler's function. Or a torsion function. So this phi of n is defined as the number, so the count of numbers less than n that are coprimed with n. These are equal, such that d and n are coprimed. So it's the set. So it's the size of this set. So for example, the 2 has a phi equal to 1, the 1 has a phi equal to close to 1. So if the number itself is coprime with itself, then it's also counted, but it only happens when n is equal to 1. And if n is equal to 9, so we have the 1 and 2 and 4, and 5 and 7 and 8. So we have 6 numbers. Let's see also this goes. So if it's a prime number, like let's say 13, so all the numbers from 1 to 12 are coprime. So it's like that. Actually, the phi of p equal to p minus 1. So this is a special case we have that gets the Fermat's little theorem. But so this is the more general version. So basically, to get the inverse, here we have this here grown to 5n minus 1. So this is another way to calculate it. So it's to get the 5n and compute this exponentiation. So here I'll just give the formula for the phi, and I will explain it in one of the later lectures, why is the formula like that and why is this theorem true. It's called the Euler's theorem. So basically the formula for a number n that is written like the product of primes. So it's a multiplicative function, which means that we can distribute the function on different coprime numbers. And each of those is equal to the number of coprimes. If we have two coprimes with this number, so it's all the numbers in this range from 1 until this number, but we have to exclude all the multiples of p's. So basically, here we divide this number by p, so we get p1 to the power p1 minus 1. So this is the count of all the numbers from 1 to this number, such that these are coprimes with the number here. So basically, if they don't have p as a divisor. And so on. So basically, this is the formula to compute the Euler's torsion function. We'll get to that later. So I'm done for now. So thanks for watching.